Okay, we are doing our last equilibrium topic. Exit ticket 15.3 goes with Ksp and equilibrium. We are going to talk about solubility of solid crystals in water, and we've talked about this before. We've described saturated solutions using a graph like this, and we talked about grams of solute in 100 grams of water. You can also talk about that as in terms of grams of material dissolved in liters of water or moles of material dissolved in liters of water, all of which are valid. We're going to look at saturation of solutions through an equilibrium point of view. Before, we only described ionic compounds as soluble or insoluble, and that was really useful at the beginning of the year when we were trying to determine what precipitate was forming in a double replacement reaction. But because we're at the end of the year, we can handle a little bit more sophistication. So we're going to talk about the solubility product, Ksp, which is the constant for the dissolving of solids in water. We can see from the graph that the solubility changes with temperature, and so we expect Ksp to change with temperature too, just like it does for all the other equilibrium systems. The equilibrium constant, Ksp, that describes the solubility of a salt, the amount that will saturate a solution. So we're talking only about the point of saturation, which is the graph before. These are saturation lines. So we're talking about the saturation at a particular temperature. It's defined this way. We look at a solid ionizing into a cation and an anion, and given this equation of dissolution of a, let's see, we're going to call that a metal and nonmetal or ionic compound, the Ksp will be equal to the concentration in moles per liter of the cation raised to the power of its coefficient times the concentration of the anion raised to its coefficient as a power. The reason we don't put the solid into the equilibrium constant expression is because solids never go in, neither do liquids. Remember, the brackets mean concentration in moles per liter. So we haven't talked about the equilibrium before in a solution, but imagine in a beaker we've got liquid and we've got a bunch of crystals in the bottom, and above that we've got ions. The ions in solution are often recrystallizing into these solids as these solids are ionizing. When we get to equilibrium, that's what's happening. If you're just looking at that beaker, it doesn't look like anything's changing, but on a molecular scale, there's ionization and recrystallization going on in equilibrium with each other. So we're going to talk about how we solve problems using this concept. Examples of writing solubility product expressions in dissolution reactions. Write the balanced chemical equation and the Ksp equation using these rules to describe the dissolving of the following salts. Let's start with silver chloride. It dissolves into silver +1 and chlorine -1 through this reaction. Noting that this is a solid, which won't go in the equilibrium expression, the equilibrium expression for Ksp equals the Ag ion concentration times the chlorine ion concentration. Remember, the brackets means moles per liter. Barium sulfate, it follows the same kind of pattern. It gets trickier when we have something that ionizes in a 1:1:2 ratio. Now we have a power in our equilibrium expression. The concentration of the chlorine gets raised to the second power because there are 2 moles for every 1 mole of solid that dissolves. So here are the steps. You want to get these down on your exit ticket. First, you write the reaction to find out, are there going to be coefficients that turn into powers when you do the math? 2, set up the Ksp expression correctly using all the Ksp rules. All the rules for equilibrium apply. And use what's given to solve. So if solubility is given, make sure it's in moles per liter. If it's in grams per liter, you have to convert it to moles first and calculate the Ksp. If the Ksp is given, you're going to calculate the solubility in moles per liter. So here's a sample problem, calculating Ksp from solubility. Copper bromide has a solubility of 2.0 times 10 to the -4 moles per liter at 25 degrees Celsius. Calculate the Ksp for copper bromide at 25 degrees Celsius. Copper bromide solid goes to copper ions and bromine ions, which are aqueous. So the point here is that the solubility of 2 times 10 to the -4 moles per liter actually means that the copper and the bromine are both at that concentration. That means we added 2.0 times 10 to the minus 4th moles to a liter of this solid. We measured out the gram molecular weight and found 2.0 times 10 to the minus 4th moles worth of mass and added it and then ionized equally in a 1:1:1 ratio. So here's how we write the equilibrium Ksp. Cu ions times bromine ions concentration. They're both equal to each other because for every mole of copper bromide that ionizes, we get a mole of Cu and a mole of Br, so they are equal to that same concentration. That's how it works. It's beautiful. It's actually really simple math. So you just multiply or square the concentration, and there's no units because equilibrium constants are unitless because all the molarities cancel each other out. All right, here's another problem. This one's a little more complex. Sample problem, calculating Ksp from solubility in grams per liter. Now we're given grams. Wait, we want it in moles per liter, but we know how to handle that. We know how to convert grams to moles, so here's how you do it. First, we're given the problem. Calculate the Ksp value for barium sulfate if the solubility is 0.00910 grams per liter at 25 degrees Celsius. So you're going to write the equation out just to make sure there's no coefficients, that the charges don't lend themselves to coefficients. Polyatomic ions stay covalently bonded to each other. You convert to moles. So you're given your concentration in grams per liter. You multiply that by moles over grams to get grams to cancel out, and you'll be left with units of moles per liter, which is this capital M. That's moles per liter. This 233.4 grams comes from the molecular weight of barium plus sulfur plus 4 oxygens. Add that up, it's 233.4. Once you've done that, then you use this concentration for each of the two ions, the barium ion and the sulfate ion. Ksp equals 3.9 times 10 to the minus 5 times 3.9 times 10 to the minus 5. And it equals 1.5 times 10 to the minus 9. No units, naked numbers, they're allowed. Next, calculating solubility from Ksp. Now you're given the equilibrium constant. It's 1.5 times 10 to the minus 16 for dissolving silver iodide. So let's find out what we've got. First, we write our equation, make sure it's a 1:1 ratio. Then the Ksp, we set that equal to the equilibrium concentrations. We know that this is equal to this, so we call each of them x. So they become x squared. 1.5 times 10 to the minus 16th equals x squared. So if we take the square root of this baby, we will get the concentration of each of the ions. So square root of 1.5 times 10 to the minus 16th is 1.2 times 10 to the minus 8 moles per liter. Now we have a unit in our answer because it's a concentration. The concentration listed is the solubility. This is how much material will saturate 1 liter of solution. So let's just notice too that the problems become significantly more complicated if the ion ratios are not 1:1. That's why we're going to write out each chemical formula and equation. In this case, the CaCl2, when it dissolves, would give you Ca plus 2 ions and 2 Cl minus ions, and then the math would be more awkward. But we're not dealing with those in this class. We'll save it for AP Chem. One more example, just for kicks, because I love calcium carbonate, and you guys know eggshells don't dissolve in water. Oh, but they do. So now this idea of something soluble and something is insoluble, and these rules we learned don't quite apply. You realize it's an oversimplification, because calcium carbonate, eggshells if you will, or snail shells, will dissolve at 25 degrees Celsius. 3.7 times 10 to the minus 15 is the constant for that equilibrium. That's a small number. So this really doesn't go to completion. This really favors the reactants and not the products because it's such a tiny equilibrium constant. So when we look at it, we're going to take the calcium carbonate, ionize it into calcium carbonate ions with a Ksp that's tiny, 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 tiny. In that reaction vessel, we would get a very small amount of material. 6 times 10 to the negative 8 moles of material of each of these ions at 25 degrees Celsius. Now you know we can up that number. That concentration will go way up if we add an acid or put pressure on the system or any other way that we can get carbon dioxide pushed into that liquid to make carbonic acid. Will dissolve the calcium carbonate and make a really cool system to study. Natural waters have calcium carbonate in it. The snails are fine. Snails and clams are fine because the product constant for solubility at normal temperatures and pHs is 3.7 times 10 to the minus 15, so they can make shells. So that's it. That's all the new material. And now you get to do homework. The homework tonight is in the packet. It's actually, even though this is a chapter 15 presentation, the worksheet that goes with it is worksheet 17.4. There's 2 pages. So good luck with that, and see you in class.